Level 0. Dust devils. Dust devils are not tornadoes despite their appearance. They form under clear skies when intense solar radiation heats the ground surface, causing the air directly above it to warm rapidly and rise. This creates thermal convection in calm conditions. When this rising air begins to rotate, often triggered by wind shear near the surface or variations in ground heating, a visible column forms as dust, leaves, and small debris get caught in the rotation. The mechanics are purely thermal. The ground absorbs solar energy and heats the boundary layer of air. Hot air is less dense than cool air, so it rises. If there's any slight directional change in the wind near the surface, that rising column can start to spin. The spinning motion creates a visible funnel as loose material gets lofted into it. This is fundamentally different from tornado formation, which requires thunderstorms, moisture, and wind shear at multiple atmospheric levels. Dust devils are most common in desert regions and during the hottest parts of the day. They typically form on barren surfaces, parking lots, dried fields, sandy areas, where dark ground can reach extreme temperatures. They're strongest in the American Southwest and Australia, where conditions consistently produce them from spring through fall. Most dust devils are weak and harmless. They may reach 100 feet tall and last only a few minutes. However, stronger dust devils have been documented reaching several hundred feet in height with winds over 60 miles per hour. These stronger vortices can topple trash bins, flip light lawn furniture, damage weak sheds, and occasionally knock people off their feet. Several cases have been reported of dust devils removing roofing material or tearing corrugated metal structures. In rare cases, dust devils have caused minor injuries, particularly in regions where they form frequently and reach higher intensity. The key distinction is their ground-based nature and thermal origin. No storm clouds are involved. No updrafts extend from the cloud base. Just thermal energy and surface wind combining to create something that resembles a tornado but operates under completely different atmospheric principles. Level 1. Gustnadoes. Gustnadoes form along the gust front of thunderstorms. A gust front is the leading edge of cold, dense air that a thunderstorm pushes outward as it develops. When this mass of cool air hits warm air at the surface, rapid vertical wind shear develops. This shear can tighten into small, short-lived rotating vortices. The mechanism is fundamentally different from tornado development. Gustnadoes do not connect to the cloud base above. They exist only at the surface and within the lowest few hundred feet of the atmosphere. They typically last only a few minutes and rarely cause severe damage. Most produce winds under 70 miles per hour. However, individual gusts can down tree branches, peel shingles from roofs, and scatter debris. During a derecho, a particularly severe, fast-moving windstorm that can stretch across multiple states, Gustnadoes form in swarms along the leading gust front. In the 1998 Midwest derecho, dozens of Gustnadoes formed in succession, creating a wall of chaotic wind impacts. Satellite imagery and radar reflectivity patterns from that event showed clear evidence of multiple rotation centers along the front, each producing localized wind damage. Gustnadoes are deceptively dangerous despite their weakness. They're hard to distinguish from weak tornadoes without trained observation. They can develop with almost no warning, making them a hazard for people in open areas or along highways. A person caught on an exposed road during an active derecho might experience multiple Gustnado passages in quick succession, each bringing sudden wind intensification. Level 2. Waterspouts. Waterspouts are tornadoes that form over water or touch down on water before reaching land. There are two distinct types, each with different formation mechanisms and hazard profiles. Fair-weather waterspouts form in relatively calm conditions over warm water, typically in tropical and subtropical regions. They develop when the air above warm ocean or lake water becomes unstable, meaning warm, moist air near the surface is overlaid by significantly cooler air aloft, creating buoyancy. Individual cumulus clouds can spawn fair-weather waterspouts without any associated severe weather. They are typically weak, lasting only 10 to 20 minutes, with winds rarely exceeding 50 miles per hour. Fair-weather waterspouts are common sights in the Florida Keys, the Mediterranean, and other tropical seas. They're visually striking, thin, white spirals of condensation extending from cloud base to water surface. They usually dissipate over open water with minimal impact. Tornadic waterspouts are fundamentally different. These form from powerful thunderstorms, just as land-based tornadoes do. The mesocyclone rotation aloft develops over water instead of land. When the tornado funnel descends and touches down on the ocean or lake surface, it becomes a tornadic waterspout. These retain the wind speeds and destructive potential of their parent supercell tornado. When a tornadic waterspout comes ashore and crosses land, it becomes a conventional land-based tornado capable of significant destruction. Florida experiences the highest waterspout frequency on Earth, with hundreds documented annually off its coasts. This results from warm Gulf Stream water, moisture availability, and frequent thunderstorm development during summer months. The Great Lakes also experience notable waterspout activity, particularly Lake Superior and Lake Michigan. Historical records document major waterspout outbreaks, including a 1969 event over Lake Pontchartrain in Louisiana, where dozens of waterspouts developed in a single afternoon. For maritime operations, tornadic waterspouts pose serious hazards. A waterspout approaching a boat or ship offers no basement to shelter in, no sturdy structure for protection. Even small tornadic waterspouts, those producing winds of 100 to 150 miles per hour, can capsize vessels, destroy rigging, and cause loss of life. Coastal communities vulnerable to tornadic waterspout landfall must maintain storm awareness and evacuation protocols. Level 3. Landspouts. Landspouts are true tornadoes with a distinctly different origin than classic supercell tornadoes. Instead of developing from a mesocyclone aloft, landspouts form when a thunderstorm's updraft stretches and tightens pre-existing vorticity that already exists near the ground. This vorticity often develops along boundaries. The dry line in the Great Plains, for example, where moist air from the Gulf meets dry desert air. Visually, landspouts appear as thin, rope-like funnels, often disconnected from visually impressive storm clouds. They may descend from relatively benign-looking cumulus clouds that don't produce heavy rain or severe weather elsewhere. This is part of their deceptive nature. A trained observer might see a sunny afternoon sky with small cumulus clouds, then watch a funnel suddenly develop with little warning. Most landspouts rank as EF0 or EF1 on the enhanced Fujita scale, producing winds of 70 to 110 miles per hour. They cause damage consistent with this intensity. Shingles removed from roofs, tree branches snapped, mapped, light structures damaged or destroyed. However, some landspouts have been documented reaching EF2 strength, with winds exceeding 110 miles per hour, capable of removing roofs and overturning vehicles. Landspouts are notably difficult to forecast or detect. They develop rapidly, sometimes forming to ground level within seconds. Doppler radar cannot always resolve them, especially weaker ones. They often occur ahead of larger supercell tornadoes, making them a surprise hazard in outbreak scenarios. The American Great Plains, particularly Colorado, Wyoming, and Kansas, experience regular landspout activity during spring and early summer when atmospheric conditions favor their formation. In 2019, Colorado experienced a notable landspout outbreak with multiple tornadoes developing from a single storm system. Observers reported funnel clouds forming, descending, and reaching ground level in rapid succession across open terrain. Each tornado caused localized damage but moved quickly and remained relatively weak. The speed of formation made warnings challenging, even for areas receiving severe thunderstorm watches. Level 4. Satellite tornadoes. Satellite tornadoes are secondary tornadoes that rotate around a larger primary tornado. Both develop from the same parent supercell, but they form in separate circulation centers within that storm. The satellite tornadoes typically remain smaller than the parent, but can still produce significant winds and damage. The danger of satellite tornadoes stems from their unpredictability. People in the path of the main tornado receive warnings and understand the threat. But satellite tornadoes often touch down outside the primary damage path in areas where residents believe they're safe. This creates a false sense of security that ends when a secondary funnel suddenly develops nearby. The 2004 Hallam, Nebraska tornado exemplifies this hazard. That parent tornado reached EF4 strength and grew to over a mile in width, producing winds estimated above 200 miles per hour. Alongside this monster tornado, satellite tornadoes touched down. extending the area of tornado damage far beyond the main funnel's track. Some residents who had escaped the worst of the main tornado were subsequently caught by satellite funnels. May 2013 in central Oklahoma saw another well-documented satellite tornado event. Multiple violent tornadoes developed from a single supercell, with witnesses and storm chasers documenting smaller funnels orbiting around the main circulation. Each satellite tornado produced significant damage independent of the parent. The total impact zone sprawled across a much larger area than any single tornado would have created. The psychological impact on survivors is notable. Being struck by an expected primary tornado is terrifying. Being struck by an unexpected satellite tornado, which appears to come from nowhere, adds a dimension of surprise and bewilderment that compounds the trauma. Level 5. Multiple vortex tornadoes. Multiple vortex tornadoes contain several intense rotating vortices spinning within the main funnel. Each subvortex can be hundreds of feet in diameter and capable of producing wind speeds as high as the strongest supercell tornadoes. The damage pattern from multiple vortex tornadoes is characteristically jagged and irregular. One house may be completely obliterated, walls removed, foundation exposed, debris scattered across the landscape. The next house, just 50 feet away, might suffer only broken windows and shingle loss. This extreme variability in damage occurs because the subvortices carve narrow paths of extreme destruction, while areas between them experience less intense winds. The 2013 El Reno tornado in Oklahoma remains the widest tornado ever recorded, reaching 2.6 miles in diameter at its maximum extent. Storm chasers and radar operators documented multiple vortices within this massive circulation. Wind speeds in individual subvortices were estimated to exceed 300 miles per hour based on the intensity of structural damage. Even seasoned researchers were caught off guard by the storm's sudden shifting behavior. Tragically, several prominent tornado researchers, including Tim Samaras, were killed when the storm shifted its path unexpectedly. The 1974 super outbreak on April 3rd and 4th included multiple vortex tornadoes, particularly in the Xenia, Ohio tornado. That tornado was rated F4, equivalent to EF4, and caused catastrophic damage. The destruction pattern revealed clear evidence of multiple vortex activity, with some neighborhoods nearly erased while adjacent areas suffered comparatively less damage. Multiple vortex tornadoes are extremely difficult to identify in real time. While Doppler radar can show the broad circulation, detecting individual subvortices remains challenging. For anyone caught in the path, survival can depend on whether a subvortex passes directly over your location or misses by a distance of just tens of feet. This introduces an element of pure chance to survival outcomes. Level 6. Supercell tornadoes. Supercell tornadoes are the most powerful, longest-lived, and most predictable type of tornado. A supercell thunderstorm is characterized by a mesocyclone, a rotating updraft that can extend many miles into the atmosphere. This deep rotation is fed by strong vertical wind shear and buoyancy within the storm. When the mesocyclone tightens aloft and reaches the surface, a tornado is born. Supercell tornadoes can last for an hour or longer, traveling over 100 miles. They produce the strongest winds on the enhanced Fujita scale, F4 and EF5 tornadoes with winds exceeding 200 miles per hour. At these wind speeds, structural damage becomes obliteration. Homes are not damaged, they're erased. Asphalt is not scattered, it's peeled from highways, trees aren't uprooted. They're snapped and debarked. Steel bridges and large structures can be severely deformed or destroyed. The tri-state tornado of March 18, 1925 remains the deadliest tornado in United States history. It traveled 219 miles across Missouri, Illinois, and Indiana in 3.5 hours, maintaining EF5 level intensity for most of its track. Nearly 700 people were killed. Multiple towns were destroyed completely. Survivors described total devastation, nothing remaining of structures in the tornado's core path. Almost a century later, this tornado still represents the longest continuous tornado track on record. The Joplin, Missouri tornado of May 22, 2011, struck a densely populated city of approximately 50,000 residents. It was rated EF5 with winds estimated above 200 miles per hour. The tornado carved a path 13 miles long and up to 1 mile wide through the city. Schools were destroyed. Hospitals suffered severe damage. Over 158 people died, and hundreds more were injured. In terms of damage per unit population, it remains one of the costliest natural disasters in recent U.S. history. What makes supercell tornadoes particularly dangerous is their capacity to generate satellite tornadoes and multiple vortices. A single supercell can produce multiple tornadoes over the course of hours, each capable of independent destruction. They can also shift course unexpectedly or intensify suddenly. Modern meteorological tools, Doppler radar, satellite imagery, and surface analysis allow meteorologists to identify supercell development. Well in advance, storm spotters can often position themselves to observe and report on supercell tornadoes. Yet the exact moment a tornado will form, precisely where it will touch down, and how intense it will become remain difficult to predict with complete accuracy until the tornado is already developing. Supercell tornadoes demonstrate the ultimate power of atmospheric convection and wind shear. They remind us that despite advanced technology and scientific understanding, nature still retains the capacity to generate phenomena that exceed human-engineered structures' ability to resist. From dust devils to supercells, tornadoes operate across a spectrum of severity and complexity. Understanding these distinctions helps explain why some tornadoes cause minor damage while others reshape geography and history. Hit like and subscribe for more weather science breakdowns.